Okay, in this video we're going to take things up a little notch and start to look at voltage and current in series and parallel circuits. So firstly, this is a series circuit and this is a parallel circuit. But before we get into this, I want to just look at really quickly what is voltage and current. And I'm going to use this picture, and I'm sorry it's a bit sort of sketchy. It's been copied off. I only have a printed version of it, but it's quite a good one. To hopefully explain what current and voltage are. So we have our battery or power pack, some sort of, a source of energy, and flowing through the circuit we've got electricity flowing through the circuit. And we've got a resistor here, a bulb here, an ammeter down here, and then another resistor over here. So what happens is that for there to be a flow of electricity, we need some charge. In this case, it's usually electrons that flow through the wires around the circuit. So these guys here with the big E on in their head are our electrons. They're running around the circuit. Now the electrons never get used up. They never ever get used up. They just go around and around and around the circuit. So how do they actually make things light up? Well, the electrons carry energy. So although the electrons go around and round and round and never get used up, they pick up energy from the battery and they carry that energy, and that energy gets used every time they go through a resistor or a lamp or some other circuit component. So they pick up energy at a battery or a power pack, and they use that energy, or that energy is converted into something else like heat or light, every time they go through a resistor or a lamp. So you can see our electrons here leaving the battery. I've got plenty of energy to spend in this circuit. So have I. Then they go through the resistor. Oh, that resistor took a lot of my energy coming through here. This light will take a lot more. This energy won't. What does it say here? Ammeter won't need much energy. Ammeters don't use very much at all. And then they have to spend the rest of their energy when they go through this last resistor, and all the energy is used up before they return to the battery. So current is the flow of electrons, how fast they flow around. And so current is never used up. If you measured the current at this point here, how many electrons were flowing past this point here each second, it would be the same as the current down here. How many are flowing past this point each second. Because if they're going round in a circuit, if you think of this like a train going around and round in a circuit, or a series of trains, the average speed around the circuit will be the same. Or if if you're counting how many go past each second, well, once one's left, it's going to come all the way around. So the current doesn't actually disappear. No electrons get used up or disappear or leave the circuit. So the electrons, the current is never consumed, the flow of electrons. So current is how fast the electrons flow. It's a measure of how many electrons are going past a certain point each second. And voltage is the energy that is gained or lost by those electrons. So how much energy those electrons pick up in the battery, or how much energy is lost when they go through something like a resistor or a lamp. So let's have a look at our series and our parallel circuits over here. So the first question here, we've got a series circuit. How does the current at point A, so that's down here, compare with point C? So that's over here. Well, if we have a quick look at this and we think of our electrons, so we've got some of our electrons over here, all right, flowing around. So those are the guys with the E's on their heads. All of those electrons make it over to this bulb, and all of them make it then over here in between the bulbs. So remember, it's just the energy that they're carrying. So we could draw, this guy here would have had a big bag of energy, all right, and this one here would have had sort of still a big bag of energy, and this one would have lost some energy, so it'd have a much smaller bag. And then by the time he's gone through the second bulb, the electron will have essentially lost pretty much all of his energy, so that bag will be completely empty. So the current, the number of electrons going through at point A over here, so returning to the battery over here, will be the same as at point C, because the current will be the same at every point in the circuit. No electrons are lost or used up anywhere. The current doesn't get consumed or used up. So essentially our answer here is the current is, we just put is, it's the same. The current is the same at point A and C. If the battery supplies 12 volts, so it gives each electron or packet, a group of electrons, 12 volts of energy, what will the voltage drop be across each bulb? And so in this case, the voltage drop across each bulb would be 6 volts. And that's because an electron going through the circuit will use 6 volts of its energy as it goes through this bulb and 6 through this bulb. That's assuming the bulbs are identical, so the same kind of wattage, the same brightness. So as the electrons go through, the energy is shared in a series circuit. The energy is shared as they go through the components. What happens if one bulb blows? What happens to the other? The other bulb goes out. Oh, typo. And why is that? Basically because we wouldn't have a complete circuit anymore. When a bulb blows, the filament, so that's the little wire inside here, so electricity goes up and through this wire and back out the other side. This little wire breaks, and so we no longer have a complete circuit. So the other one would go out too. Okay, so key things for a series circuit is that the current isn't consumed, it doesn't get used up at all, so the current is the same at every point in the circuit, but the voltage is shared between components. The energy that the electrons carry is shared. The current, the rate at which they're flowing, is the same though. Alright, let's have a look at our next wee question. So if we look at a parallel circuit now, down here, how does the current at point A, so down here, compare with point C? Well, what happens here? It's a little bit different, and it's kind of actually exactly the other way around. Over here, let's say we've got 2 electrons going, or 2 groups, packets of electrons, going around the circuit each second. Well, what happens when they get to this point here? Well, they're going to split, and half of the electrons are going to go one way, and half are going to go the other way. Now that's again assuming the bulbs are identical. Electrons will always take the path of least resistance, and it's not because they're intelligent. They don't know which pathways got more or less resistance, but think of it like pushing water down pipes. If you had a pipe and it branched, it split in two, and you were pushing water down the pipe, and when it split, if one of the pipes that it split into was pretty narrow and blocked up, and the other one was pretty wide and completely clear or clean, then you would expect more water to go down the pipe that has less resistance. But in this case, if the bulbs are equal, they'll split. We'll have 2 of them here, and each of them will go, half of them will go this way and half of them will go that way. And then coming through the other side, well, remember, current isn't consumed. They don't get eaten up or used. The electrons are still there. They don't just disappear into thin air. So the electrons still are there on the other side. And when they come around, so this one flows around the side here, on the other side down here, they'll rejoin again. So we'll have 2 over here. So for instance, if we had 2 amps, which is basically 2 packets of electrons. Electrons are measured in packets called coulombs. They're too small to deal with just 1 or 2. If we had 2 packets of electrons here, one would go this way, one would go that way. They'd rejoin again, we'd have 2 here. So how does the current here in A compare with either of these branches? So for instance, point C over here, well, we would have half the current. So the current splits, and we could say point C has half the current. So current splits in a series circuit. It splits between the branches. Now, if the battery supplies 12 volts, so we're imagining again that each of these guys here have a nice big bag, let's say that's got 12 volts of energy in it, they're carrying 12 volts of energy, how much voltage, what is the voltage drop across each of these bulbs? Well, because each of these electrons, as they go through this bulb, they're not going to go through the other one. So each bulb receives the full voltage. We get the full 12 volts that the electrons are carrying being lost here, and these ones are carrying 12 volts. They lose the full 12 volts as they go through this bulb too. And they always return, so electrons always return empty-handed to pick up more energy from the battery again. So in this case, if the battery supplies 12 volts, what is the voltage drop across each bulb? So in this case, it is 12 volts. They both receive the full voltage. So in a series circuit, the current doesn't split because it all just goes around the circuit. It doesn't get used up, but the voltage gets shared. The electrons use half their energy, or the voltage, half of it gets lost at the first bulb, and the other half gets lost at the second one. Again, assuming they're identical. In this circuit, the current is actually split. Half the electrons go one way and half go the other one. So think of current like current in a river. It's the flow of water. Here it's that flow of electrons. If you jumped in there, you'd be pushed by those electrons. They get split. The current would be half as much in each branch as it is before the split and after the split. But the voltage, each bulb gets the full voltage. So this last question here, 5C, what are the advantages and disadvantages of arranging bulbs in parallel rather than series? Well, one advantage in a parallel circuit here, if each bulb gets the full voltage, the bulbs are brighter because they're getting more energy. But that means one of the disadvantages is the battery will go flat faster. Because if the bulbs are brighter, they're using more energy, the battery will go flat a little bit quicker. And lastly, one other advantage in this case, if you can imagine, if this bulb blows, then the other one will keep going because there's a separate pathway that the electrons can flow through. There's still a complete circuit. So advantages, the bulbs are brighter. If one goes out, the other one keeps going. But the disadvantages, the battery does go flat a bit quicker. Okay, so I hope you found that helpful. It's definitely something a bit tricky to get your head around, but it's really important you've got a good understanding of what voltage and current is. So voltage is the energy gained or lost by each packet of electrons as it goes through an energy source. There'll be energy gained, or the energy lost as it goes through some circuit component like a bulb or a resistor. And current is the rate at which the electrons which carry the energy are flowing.